Time to discuss time dilation. Remember what I was saying just before, that every observer observes time differently than everybody else. Let's investigate this. We're not going to do the entire mathematical proof in this section. You can go through that yourself, but we're going to cover on the high points on this. So let's say that I set up a experiment, the speed of light measurement. I'm going to have a little laser here. Boop. It shines the light, dun, 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 hits the mirror. There's a mirror at that end, and then it comes back. Dun, 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 dun. Cool. So that's cool. So I can measure the speed of light, and if I do that, I know the distance, I know the time. I measure it as, I don't know, 3 times 10 to the 8 meters per second, approximately. But say this is in, but say I did this experiment in a spaceship. So I'm doing the same thing. I have my laser and I send out the beam of light and it hits the mirror and then it reflects back. What happens here is the light actually travels like this, and then reflects. Now, to me, it looks like it's just done that. This is the same thing as throwing a ball in a train. Remember the whole tossing the ball or dropping the ball? I see the ball, or this in the case, light go, let us bounce, and come bounce back. But if I was bouncing a ball on the train, you'd see it go bounce and travel along. Same thing. But remember, what we've said is the speed of light is constant. Speed of light is constant. So C equals approximately 3 times 10 to the 8 meters per second. But here's the concept. So what's the velocity? Velocity is equal to distance over time. So the distance here, the velocity c is the same. And this is one of the fundamental rules of Einstein. Well, this is Einstein's postulate. If I measure the speed of light here, I see it go bounce, and I measure it doing this. If I'm standing outside here, watching this go past, boom, boom, this light is still travelling at this speed. But the distance it's travelled is further. Because in the person inside the train, all I see is the light goes bing, bing, and it's gone this far. But now, to me, it's gone this far. And that's actually a lot further. So how is this possible? How can this be the same if these are different? And the answer is because the time is also different. These two people, the person in the train or in the rocket and the person outside, are experiencing time differently, which allows them to see the speed of light the same. And we're not going to go through the whole derivation, but basically what we can actually find out is that there's a time factor. So what we actually work out is basically the time one person sees, the time is going to equal the least time, the observer time, I'm going to call this proper time. So this time multiplied by what we call a gamma factor or a Lorentz factor. And if you sit down and work this Lorentz factor out, so time is equal to gamma. So what is this gamma factor? Well, you can go through the notes and it does the complete derivation of it for you, but basically the gamma factor is equal to 1 over the square root of 1 minus v over c. And for convenience's sake, v and c are measured in units of c. So basically what this means is, so for v, take the value equals v in the units of c equals v divided by 2.998 blah 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 times 10 to the 8 meters per second. So we basically figure out what proportion of the speed of light is that velocity. And it's going to be a number between 0 and 1. Well, yeah, because we haven't figured out a way of going faster than the speed of light yet. Theoretically you can, but nobody's figured out how to go faster than the speed of light without travelling at the speed of light first. So if you figure that out, Nobel Prize time. But then part of the reason for doing this is it makes this a lot easier. Now we just have c divided by that is going to equal 1, and that's going to equal some value between 0 and 1. It just makes the maths a hell of a lot easier. I know we've got calculators nowadays, but... So basically what we do is we take the proper time. So we call that the gamma factor. It's a Lorentz transform. So what we're going to do is we're going to take the proper time T naught is the least time, the smallest of the two times. Two times. And so that's going to usually be, so usually it is the time for the travelling object of the travelling object, because the travelling object would usually experience time slower than the standing object. So this seems weird, but does this actually work? And one of the very earliest proofs of this, well, one of the first proofs that this is all right was basically they didn't find ether, but also one of the first proofs was the planet Mercury. If you look at the planet Mercury, you got the sun, and the sun is a big hot burny thing, and you got the planet Mercury travelling around there. Mercury is a small planet. It travels at what, about 43 kilometers per second. So Mercury V equals 43 kilometers per second. Because it's so close to the sun, because it's so close to the sun, it's actually travelling really fast. And the orbital period should be, if you actually sit down and work it out, it should be 7,603,200 seconds. Cool. However, that's the time predicted. The time actual that we actually measured was 7,603,807.6 seconds. So what actually happened is, in one orbit, each orbit takes about 10 minutes longer than the physics of the day predicted. So back in the 1800s, late 1800s, they knew they had a problem, because they said it should take this long, but actually takes Mercury 10 minutes longer to orbit than they predicted. And their first thought was that there must be another planet out here somewhere. So a little planet called Vulcan. That's what they actually called it. They called it Vulcan. And so they said, yeah, there must be a planet out there. And they kept looking and hunting for about 40 years. And there were sightings of Vulcan, which were probably just asteroids flying past. And then they applied Einstein's relativity to it. And Einstein's law of relativity basically predicted that on the planet, one orbit takes 7,603,200 seconds. So if you're on the planet, it will take that long to do an orbit. However, to the outside observer, it takes 10 minutes longer. And that's because of the time dilation effects that we were just talking about. If you use this formula here, you stick it through the equation, it gives it almost perfectly. And this was actually one of the earliest proofs that Einstein was actually onto a valid and good idea. And in fact, this same problem actually happens with GPS satellites. If we have GPS satellites, what the satellites have on board is a very accurate, so just put some solar panels on, they have very accurate atomic clocks. And what you're doing is you're measuring the time difference between signals and such like, but these are actually moving. And you actually get this time dilation effect. These are in a slightly different time to each other. So for the GPS system, they actually had to write encoding and things to take into account the relativistic effects of the movement of these. Okay, so let's actually do a couple of examples. Okay, so example 7.2. Let's try this. Muon decay. Okay, muon is a subatomic particle. Muons are elementary particles of the same charge as an electron, but a mass 207 times greater. Okay, that's cool. They're produced by collisions of cosmic rays, which are really high energy electromagnetic waves, in the upper atmosphere, 12 kilometres above the Earth. So basically you have a gamma ray come in, they hit something, boom, like an atom or something, and then they'll spit out this muon, woohoo, and away it goes. And this is about 12 kilometres up. Now, the muons, these, as a rule, yeah, this subspecies muons are very, very, very short-lived. So a muon will have a time of 2.2 times 10 to the negative 6 seconds. That's a fairly short life expectancy. And so if you actually work out distance equals velocity times time, how fast are they going to say? It's going to travel about 660 metres. We'll probably prove this in a second. So basically, the muon travelling really fast, almost the speed of light, I mean we're talking like 0.999 times the speed of light, will travel 660 metres in its lifetime because it only lasts for a very short time. However, we can actually observe these things hitting the surface of the Earth. We can actually put detectors out that measure the muon hitting the surface of the Earth. And how is that even possible? Because it should only last 660 metres. And that's because, but there's a relativistic effect going on. So V is equal to 0.999 C. So the V going on, it's going to be that. This is going to be the proper time. This is going to be the short time, because if it's going more than 660 metres, there must be two different times going on. There must be the time for the muon and the time for us watching it. So how long does it take? Well, basically in the time frame, D, let's work it out. D is equal to Vt. So this TO, this is for the muon. So for the muon, what happens is that we work it out, D is equal to, V is going to be 0.999 C times 2.998 times 10 to the 8 meters per second C per C times the time 2.2 times 10 to the negative 6 seconds. So for the muon, 0.999 times 2.998 x 8 times 2.2 x minus 6 equals, so the muon thinks sees it's gone 658.9 metres. Isn't that cool? But what about for the observer, outside observer? For an outside observer, we see the time differently. outside observer, what we then see is we see time is equal to gamma times the time the muon sees. Remember, the t naught is usually the thing that's going to be moving. It's the time, it's the shortest time. So how do we do this? Well, so t is going to equal, the gamma factor is going to be 1 over the root of 1 minus b squared over c squared times t naught. So that's going to equal 1 over the root of 1 minus 0.999 squared over 1 squared times, what's the time? Time is 2.2 times 10 to the negative 6 seconds. And at this point, this is what we invented calculators for. So we go, let's take it out, we go 1 minus 0.999 squared. We should divide that 1 by 1, but you divide it by 1, it's going to be equal to itself. 1 minus 0.9999 squared, okay, oh yep, that's right. And then what we're going to do is we're going to take the square root of that, square root the answer, equals 0.0447, and then we're going to take the inverse of that, inverse, equals, so time, and then we go, so that's the gamma factor, times 2.2 x minus 6 seconds. So for the observer, for us, we actually see that the gamma, this particle actually exists for 4.9206 times 10 to the negative 5 seconds. So for this particle, in its time frame, it lasts 2.2 times 10 to the negative 6, but we see it as 4.920 times 10 to the negative 5 seconds, so it actually lasts a lot longer. And so now we stick it in, d is equal to vt, and notice that was for the object, this is just for us. So distance is equal to velocity, which is going to be 0.99999c times 2.998 times 10 to the 8 meters per second per c times 4.9206 times 10 to the negative 5 seconds equals 9 times 2.998x8 equals 14,737 meters. So basically, the muon, for the muon, it's only travelled 660 meters. We see it travel 14,737 meters. And the reason why this happens is because the time for the muon and the time that we see it are different. Time exists at a different rate depending upon your velocity. And if that doesn't hit your brain, we'll try in the next one.